Okay, now we're going to talk about nuclear chemistry, which is our next module and the last part of module 1. Okay, and so let me tell you a little bit about the other parts of the atom. We spent a lot of time talking about some of the experiments that were used to describe what an atom looks like, and then we went on to the energy levels for the electrons and orbitals and hybridization and molecular orbital theory, and a lot of that had to do with the electrons. Okay, so now let's go back to the nucleus and see what's going on in the center. So it turns out that different nuclei are stable under different situations. Okay, so here's a graph that somebody created who had a lot of free time on their hands. And basically what they did was they looked at the atomic number, Z, on the x-axis, and number of neutrons, N, on the y-axis. And what they did was they looked at every single element in the periodic table, and for each of those elements in the periodic table, they looked at what the common isotopes are for that element, and how many protons it has. Obviously, that's the atomic number, but also how many neutrons it has. Okay, and they saw something interesting. Okay, for the most part, you see this black line here, there was an interesting trend between number of protons and number of neutrons, namely that as number of protons increased, number of neutrons also increased. And these different colors represent something called the band or the island of stability. So these were all of the known isotopes for all of the different elements. And they all seem to fall pretty tightly within this cluster or this band or this island of stability. And it seemed that if things were not in this island of stability, they would try to achieve stability by changing somehow, some kind of nuclear reaction to fall into this band or this island of stability. You'll also notice that the black line kind of stops right around here. Okay, and so it turns out that if you go past about 84, okay, all of the nuclei will automatically undergo radioactive decay. And if you go to about 92 or so, all of these things are not natural in the sense that we can create them in a laboratory, but we can't really find them in nature. Okay, so going back to this picture, you'll notice that this black part, it's not really straight, it kind of curves a little bit. Okay, and so if I look kind of here, closer to the origin, this represents relatively small nuclei, things with a relatively small number of protons and neutrons. So here, the slope is about 1, which means that the number of neutrons compared to the number of protons is about 1 to 1. But as I go further and further out, the slope increases, meaning that there's more neutrons than there are protons. So by the time I get to the really heavy ones over here, it might be something like 1.6 to 1. And somewhere in the middle, it might be more like 1.4 to 1. Okay. Irrespective of those ratios, there are still certain nuclei that exist that happen to be even more stable than you would predict. And so these are called magic numbers. And so it turns out that if I have 2 or 8 or 20 or 28 or 50 or 82 or 126 nucleons, those things are really, really stable. Okay, so let me tell you a little bit about radioactive decay and what that means. Okay, we strive to be stable, to fall within this band of stability. And if things are not stable, they're going to try to become stable by adjusting the number of protons and neutrons so that they're within that band or island of stability. And so it turns out that we can change the ratio of neutrons and protons by doing two things. One is called alpha decay, the other is called beta decay. It's also possible to keep the ratio the same but still become more stable. That's called gamma decay. And there's other two possibilities called fission and fusion, which are actually the basis of nuclear reactions. Okay, and so fission is when you take a relatively big, heavy nucleus and you shatter it into smaller pieces, and then that releases a lot of energy and makes things more stable. Okay, fission is the opposite. You take relatively small things and you kind of glue them together to make a larger nucleus. That can also release tremendous amounts of energy and make things more stable. Okay, so let's talk about alpha decay first. Alpha decay is really nothing more than loss of a helium nucleus, which we're going to depict as 2,4He. Technically, this has a charge of positive 2 as well. Alpha decay can happen pretty much anywhere within the periodic table, but you tend to find it more often with the heavier nuclei, things that are closer to the right-hand side of this graph. Okay, and so if you look on this figure, alpha decay was in yellow. You can see a lot of the alpha decay is over here. Okay, so here's an example of something that undergoes alpha decay. You can take uranium-238 and it loses a helium nucleus, right here's the alpha particle, to generate another nucleus, that of thorium. And so let me show you how to balance these nuclear reactions. The top number is the mass number, which is the number of protons and the number of neutrons. The bottom number is the atomic number, which is really the same as the charge, okay, in the nucleus. And so if you look at a uranium nucleus, it has 92 protons in it, and 238 minus 92 is 146 neutrons. So way more neutrons than protons. But the point is that if it lost an alpha particle, the atomic number went down by 2, so this has to be 90, right? 2 plus 90 is 92. And the top number had to go down to 234, right? 238 minus 4 is 234. So when I balance nuclear reactions, I have to balance two things. I have to balance the mass numbers on top, and I have to balance the atomic numbers on the bottom. Now, beta decay is a little bit more complicated because there are actually different kinds of beta decays. And the beta decay itself could be found anywhere as well in the periodic table, but you tend to find it for things that are in the middle of the periodic table. And so we're going to talk about beta minus decay first. This is the most common example of beta decay. And beta minus decay is nothing more than the loss of an electron. Okay, the symbol for an electron in nuclear chemistry is shown here, -1, 0, E. -1 because the electron has a charge of -1, 0 because we assume the electron has no mass. Okay, so here's an example of something that undergoes beta minus decay. By the way, I should say, if all you see is the word beta decay, it's assumed to be this type of decay, which is beta minus decay. And so here is carbon-14 undergoing beta minus decay, losing an electron, to make nitrogen-14. So let's balance this. Okay, down here I have a 6. The electron has a charge of -1. So this number has to be 7 to balance those numbers, right? -1 plus 7 is 6. The top number for carbon was 14, that particular isotope. This was 0. That means that this number shouldn't change. It should still be 14. So now this nuclear reaction is balanced. Okay, let me tell you something interesting, because you might be asking yourself, wait, something is not really right here, because we're kind of focusing on nuclear reactions. This is all about nuclear chemistry. And all of this stuff is happening in the nucleus. And earlier I told you that the nucleus has protons and neutrons in it. So where the heck did these electrons come from? Okay, hopefully you're sitting down, because this is pretty crazy. Okay, it's about to rock your world. Okay, a neutron is not really its own thing. Okay, a neutron is really basically a proton and an electron that did this and fused and made one big particle. Okay, so what I'm doing in these beta decay reactions is taking this neutron that kind of consists of a proton and an electron and breaking them apart to create an isolated proton and an isolated electron. Okay, and so net, what I'm doing is converting a neutron into a proton. So here's the nuclear reaction for that. Okay, symbol on the left is that of a neutron. Okay, has no charge, right, neutral, and a mass of +1, and is being converted into an electron, -1, 0, E, and a proton, right? So the symbol for a proton is 1,1H because this has a charge of 1 and a mass of 1, and of course that's atomic number for hydrogen. Okay, and so we would tend to convert neutrons into protons when the ratio of neutrons to protons is too high, right? I want to basically get it closer to the 1.2-ish range. There's another kind of beta decay called beta plus decay, or positron emission. You say, wait, this is getting kind of crazy. What the heck's a positron? Okay, a positron is kind of like an electron, but it's not exactly an electron. Okay, a positron is called the antiparticle of an electron. You say, antiparticle? Ooh. What's that? Well, a positron has the same mass as an electron, which is to say 0, or very, very small. But instead of having a charge of -1, it has a charge of +1. Okay, and so antiparticle means that when these two things were to collide, they would basically annihilate each other. Okay, and so here's a nuclear reaction that shows beta plus decay. Okay, sodium-22 can lose a positron to create neon-22. So you notice that this is balanced, right? The bottom numbers work out, the atomic numbers or charges, and the top numbers work out, right? The mass numbers are the same. So the nuclear reaction that's happening here is I'm basically taking an electron and a positron, and they're going to collide with each other to create two things called photons, okay, or gamma decay. The third type of beta decay is something called electron capture. So electron capture is when I gain electrons, right? They're being captured. Okay, so here's an example of electron capture. I can start with arsenic-73 and gain an electron to make germanium-73. You'll notice once again that the numbers are balanced, right? 33 and -1 gives me 32. 73 and 0 still gives me 73. Okay, here I'm kind of doing the opposite of what I did before. In beta minus decay, I was taking a neutron and smashing it apart into a proton and an electron. Here, I'm going to take a proton and add an electron to it to convert it into a neutron. So this would be done if I had the opposite problem of what I had before, right? Before I had too many neutrons, I needed to convert some of them to protons. Now I have too many protons, so I want to convert them into neutrons. The final type of radioactive decay is something called gamma decay, or gamma emission. So these are going to be high energy photons that are lost. Okay, so this is the symbol for a photon, 0, 0, gamma. Okay, the 0 on the bottom is because the thing has no charge. The 0 on top is because the thing has no mass. Okay, and so this is not going to change the atomic number, nor is it going to change the mass number. Okay, and so here's an example of gamma decay. Technetium-99, which is kind of square in the middle of the periodic table, can undergo gamma decay to form technetium-99. And you say, wait, this doesn't really make sense either, because on the left side, it's technetium-99. On the right side, it's technetium-99. I didn't change the mass. I didn't change the charge. I didn't change anything. What the heck did I change? Well, the only thing that got changed is really this little m over here. Okay, little m here means meta stable. So it's stable, but it's not super duper stable. You say, well, what the heck does that mean? Okay, well, here's another one of those crazy moments where I hope you're sitting down because your world is going to be turned upside down. Okay, remember earlier we talked about electrons and energy levels and how they can move around? Okay, well, I got news for you. It ain't just electrons. Okay, things that live in the nucleus also reside in different energy levels. And so what's happening in gamma decay is the nucleons, like the protons and the neutrons that are living there, happen to be in some kind of excited state. And they're going to lose a little bit of this energy and come back down to a less energetic, more stable ground state. Okay, so that's what's happening in gamma decay. We're not changing any of the numbers in terms of atomic number or mass number, but we're changing where the nucleons live in terms of their energy levels. The last thing I want to tell you about is nuclear fission. Okay, and so this is what's known as an artificial transmutation. Okay, artificial because It's done by people and not found in nature. Transmutation is a type of reaction where we basically convert one element into another element. Okay, and so here's how nuclear fission might work. Okay, and please don't try this at home. Okay, you get your hands on some kind of element that is fissionable, that can create fission. Okay, for example, certain isotopes of uranium, like uranium-235. And you take your big uranium-235 nucleus and you hit it with a neutron. Okay, so the neutron that's hitting it is being called a magic bullet. Okay, it does magical things. When the neutron hits it, it basically causes this very large uranium nucleus to shatter and break apart into several different pieces. In this case, it's going to break apart into two other nuclei, a barium nucleus and a krypton nucleus. And in this particular example, the barium isotope is barium-141. The krypton isotope is krypton-92. When I balance the numbers, I'll notice that it doesn't quite work, right? I need another 3 neutrons on the right-hand side compared to 1 neutron on the left side to balance this, okay? So notice that for every 1 neutron that I used, I produced 3 new neutrons. Each of those 3 neutrons that I made could act as yet another magic bullet. So, and kind of each one can hit a different nucleus of uranium. So if 1 neutron can produce 3 neutrons, 3 neutrons can produce 9 neutrons, and 9 can produce 27, and 27 can produce 81, and 243, and whatever comes after that, and blah, blah, blah. You get the idea. The point is, this can very quickly create a lot of chemical or nuclear reactions, okay? And so if you're not careful, this can be a chain reaction where the number of particles grows exponentially, which is somewhat dangerous, okay? And so, again, if you're building this in your basement, I suggest you don't do this. But if you want to be safe about things, you have what are called control rods or moderator rods that are literally just giant pencils that absorb some of the neutrons so that instead of producing 3 and using all 3, you produce 3, but 2 of them get soaked up or absorbed by these control rods, so only 1 of them emerges. And so you have a more sustainable kind of 1 to 1 to 1 to 1 situation to make things a little bit safer.